This short lecture recording is for series circuits, and I just grabbed this out of the book. And then in most books what you find when they put series and parallel circuits in there as examples is 2 or 3 resistors. I figured I'm going to do 4 just so that you can see that it doesn't matter how many there are. It's just the principle that applies so that somebody doesn't get fixated on, oh, it only works for 2 resistors, and that's not true. So here are a couple more, R3, R4, trying, with a voltage V3 on there and V4 on there. Then you find a number of things that apply in a series circuit, but instead of just writing down, I figured that I'm just going to go here to Phys, Google for it, so that we can see in this animation how it works. So Google Phys, go to play with the simulations, go to physics, go to electricity, and there it is. Circuit construction kit DC only. Sure. It asked me to, if I really want to open this one here. Alright, so 4 resistors. Actually, I won't grab a wire, I will grab 4 resistors. There we go. And I will label them 40 ohms, 50 ohms, 60 ohms. Oops, actually I meant to not give it a pattern, so what did I just say? 40 and 50, 70 ohms. That was my intent to kind of have a strange number here. So 40, 50, 70, and 90 ohms. Then I'm going to put a battery here. I'm going to change that to 10 volts, I guess. Okay. And then I'm going to put in here actually a number of ammeters so that we can look at what it's measuring. So here's an ammeter on the left and one on the right. And then there's an ammeter in between here, between these two. And there's an ammeter between these two. And there's an ammeter between these two. And then, lo and behold, I actually do need a piece of wire. There we go. And we have a current flowing. And what we can see, no matter where I measure the current in the electric circuit, I always measure the same current, 0.04 amps. Remember that this one is 10 volts. So 10 volts divided by a total current of 0.04 amps is going to give me a total resistance of 250 ohms. And if you think about these numbers here, what did I say, 40, 50, 70, and 90, and you add those 4 numbers, you're going to come up with 250 ohms. Let's look at the voltage that we apply here. So there we go. 10 volts on this one here. 1.6 volts on this one here. 2 volts on this one here. So apparently the larger resistor takes on more voltage. 2.8 volts and 3.6 volts. So the 4 resistors split up the voltage according to the resistance they have. So the largest resistor gets the largest voltage, and if you look at these numbers here, 3.6 volts to the total of 10 volts is the same ratio as 90 ohms to 250 ohms. So from that we can pretty much write down what it says in the book, that in a series circuit the total voltage is all the voltages added together. That was supposed to be a plus. That the current is the same everywhere. And I guess because I took 4 resistors, I actually make myself more work. Oh well. And that the total or equivalent resistance, let's see what the book calls it. Trying to look at that. I guess actually our book calls it RS for series resistance and RP for parallel resistance. Later on I don't see the word equivalent or total. I'll just call it either one. Total resistance in series is add all the resistors. You can also see that this one here follows from the first one and the second one via Ohm's law. If I grab this one here, whoops, copy and paste, and now I apply the second one to this one here. So I'm gonna plug in here and with Ohm's law, and I say, okay, this one here is gonna be therefore I1 respectively total current 1 times total current times the resistance 1, and this one here is IR2. And if I continue doing that, and if I continue doing it properly, well, then throughout I have R1, R2, R3, R4, and R total, and I have the same current all over that divides out, and what I come up with is that the resistances add up. So as I said, this one here actually derives from this one and this one using Ohm's law. So this is an analysis for a parallel circuit, and again, usually in books you get like 2 or 3 resistors, and just to show you that it's for any kind of resistors, again I'm going to choose for myself, put some more wiring on here. Could have abbreviated that by making one long line earlier. Oh well. There's R4 and there's R3. So there we go, and then of course here's I3 and I4, and then let's see what we're going to get on this one. Okay, there, and this is going to be pretty crowded here. Alright, and get myself some ammeters. And one more if I can. And a battery here. And now this time around I need quite a few wires. sure switch. Whoops, doesn't want to get there. There we go. And close the switch. Maybe. Is it closed? What did I do now? Doesn't like the switch, or it's not connected. Maybe it's not connected. There we go. Alright. Well, for one thing, right now what we can see is there is a certain current flowing through here, 3.6 amps, and it splits up into 4 equal currents, 0.9 amps. But that could be due to that by default it gives me the same amount of resistors. So let me change the resistors. Earlier for the series circuit, I had used 40, 50, 70, 90. So I'm gonna use some arbitrary numbers here. 30, 50, 60, and 90. And let's see what we're gonna. And then do I leave it at? I think this is at 9 volts. I could leave it at 9 volts. That's all right. Okay, and there we go. And notice that the currents are quite different. In fact, it definitely looks like that the smallest resistor in a parallel circuit gets the largest current flowing through it, and then this largest resistor gets the smallest current through it. And then what we also can see is that these 4 currents add up to the total current. Right? 0.10, 0.15, 0.18, 0.30 comes out to 0.73. Okay, let's see what happens with the voltmeter. Okay, here's the 9 volts. And on this resistor, 9 volts, 9 volts, and I guess that just goes on, which makes sense that they all take the same 9 volts because all of these sides of the resistors are at the same potential. There's just a piece of wire in between, and then all the sides of these here over here, they're all of the same potential. There's just a piece of wire in between. And sure, there is an ammeter at this point, but the ammeter has such a small resistance that it can be neglected compared to the others. In fact, when we take it out and just put a piece of wire in there, you'll see that we have the same outcome here. Okay, so in a parallel circuit, everything gets the same voltage, but the current splits up into its parts. But it would be pretty hard to come up with how it actually splits up. It's not as easy as a series circuit. Let's look at the total resistance in here. Well, the total resistance can be computed if I take 9 volts and divide by 0.73 amps. So I'm going to do that. And I come up with that the total resistance is 12.3 ohms. And notice the resistances that I have in here are 30, and then again, what did I give it? 50, 60, and 90. So which means the total resistance is completely different from if I just look at these numbers here. And how could I possibly calculate them? Well, that's what this mini lecture is about. Also, what I notice is as I calculate the total resistance, it's smaller than any one of the other resistances, smaller than the smallest one, in fact the 30 ohms here, and I came up with 12.3 for the total resistance. A moment ago I mentioned that it would be kind of tough to come up with the amps here top of your head, but I was thinking in ratios like I did earlier for the voltages in the series circuit. Actually, it's not that hard if you just use Ohm's law and say, okay, I got 0.3 amps through here because I have 30 ohms and 9 volts. 9 divided by 30 is 0.3. Here I got 9 volts divided by 50 ohms, so I come up with 0.18 and so on. So actually individually doing them using Ohm's law is going to give us that result. Okay, let's look at what we have found out so far. And that is that in a parallel circuit, the total voltage trying to write this, the total voltage equals the voltage on the first resistor equals the voltage on the second resistor equals the voltage on the third resistor equals the voltage on the fourth resistor. And we have found out that the total current adds up, respectively splits up into I1 plus I2 plus I3 plus I4. And on the left in this diagram, the current is splitting up at the junction, and on the right it's coming back together. It's also called the junction rule, one of Kirchhoff's two rules. The other one is the loop rule that we'll look at in a little while in a different mini lecture. Alright, that's what we have so far. What we don't have so far is the currents. The resistances. Unlike the other one, where the series circuit, where it was pretty easy, this one here is not as easy. What I'm going to start out with here is the currents, and then I'm going to use Ohm's law on that. Copy and paste. And let's see, maybe I can give that a different color. Oops, what was that? I don't want that. There we go. Alright. I want to find out something about the resistances. So what I do here is I divide each of these currents by the voltage, and all the voltages are the same across each resistor. And I have to stop myself. What I was about to do is not going to come out. Hold on. So what I'm going to do here is I'm going to insert Ohm's law, where I have that the total current equals the total voltage divided by the total resistance. And then I have the voltage on resistor 1 divided by resistance 1, because that's the current 1. And then, again, this is all Ohm's law that I'm using here. Current through the second resistor equals the voltage on the second resistor divided by resistance 2, and so on. And notice, of course, I leave out V1, 2, 3, 4 and total, because according to this one here, they're all the same voltages. So I just write V. There we go. And now what I do is, since the voltages on each of the resistors, including the total voltage, is everywhere the same, all of this divides out. And if I really wanted to, I could change the color on this one. Purple. So all of this divides out. Divide each one by the voltage. Oh, and then I don't know how to do purple here. Oh, actually I do know. There you go. As it divides out, of course, I'm left with a 1 in the numerator. And I pretty much did the same thing as I did for the series circuit. I used these two here for the voltages and the currents, and used Ohm's law to derive how the resistances add in parallel, which is add the reciprocals and then take the reciprocal again. Let me show you. I did that on the series circuit before. Even though here it was obvious what happens to the resistances, we could see that in the simulation circuit. But I pretty much did the same thing here. I looked at the voltages and the currents in the series circuit, combined them down here, and then kind of sleight of hand showed that the current is dividing out, and I come up with how the resistances add. And so using Ohm's law, and that's basically what I did here. Okay, let's see what happens with our particular numbers that I gave. So I'm going to write these down here. That was 1 over 20 ohms. That's not true. That was 1 over 30 ohms, right? That was my first one. And the simulation plus 1 over 50 ohms plus 1 over 60 ohms plus 1 over 90 ohms, and that equals 1 over the total. And then I should write example here. That was supposed to be a colon. Equals something here and some kind of unit. I forgot ohms here. I open the calculator. Alright, plug in these numbers, 1 over 30 and so on. And you can see I will come up with a pretty small number because I'm adding the reciprocals. .0811 and so on. 0.08111 and so on. And the unit is actually, because the ohm is in the denominator, ohm to the -1. That small number here should always remind me that I still need to invert that in order to come up with what the total or equivalent resistance actually is. So I still have to take the reciprocal of that one. I point that out strongly because that's a typical mistake that is being made. Oh, I got it. Well, you have forgotten to take the reciprocal of it again. So to -1. And that's what I had calculated earlier when I had looked at this kind of circuit and said, I take the total 9 volts here divided by 0.73 amps, and my calculator gives me those 12.3 ohms. And that's basically it on how resistors add in parallel, and that the currents add as well as it go through junctions, and that the voltages are the same across each resistors that are in parallel. This is a mini lecture on analyzing a more complex series parallel circuit. And I got this from a different book, so I'm just going to put the schematic onto the circuit here. There's a 9-volt battery with an internal resistance of 0.5 ohms. I'm going to hook an ammeter right next to that. And then I'm going to put a piece of wire. And then I'm trying to grab this resistor. There you go. And of course I could have all prepared this already, but I figured I might as well record that here so that you perhaps entice you to use this construction kit at Physics Educational Technologies as well. because of course, as you can see, it is kind of fun to play with. Okay, I'm thinking that I might run out of space here. Let's see. And then of course I still have to change all of these. Not done yet. Oh, I do have a complete circuit. Okay, maybe not as pretty as in a book. Okay, last resistor here and a couple more wires. There we go. And at this point, don't pay attention to the measured electric current because I need to change all the resistors according to this schematic that I got from a different physics book. So you can see what I put in here. Okay, and actually if I click on show values here, oh, there we go. Much nicer. Well, almost an overkill, but at least that way we can see what we got. These two down here are 5 each. That's a little weird. I don't remember clicking this here to leave the value out. I'm going to pause this here for a moment. Okay, I don't know why. Turn the values off anyway. Let me just check against the schematic that I have in front of me. That I got all the values here correctly. Okay. So here we have a number of resistors that are in parallel and or series, and we have to figure out what the equivalent or total resistance is. We can already figure it out because I put an ammeter in here. So all I have to do is 9 volts divided by 0.89 amps, and that of course comes out to 10.1 ohms, or perhaps around it 10 ohms. So keep that in mind. When we're done with this, we should come up with 10 ohms, because according to Ohm's law it's 9 volts divided by 0.89 amps, which is 10.1 ohms. Okay, let's analyze what's going on here. These two resistors are 5 ohm resistors. They're in series. These two are in series, and then these two are in parallel with this. This one here, the 6 ohm, is in series with these three, and then this whole thing here is in parallel with these down here. Okay. Then these two are actually in parallel with each other, and then finally all of this here is in series with these two, and with this one, and with this one. So what I'm going to do now is I'm going to follow what they have shown you in the book on how to analyze the circuit, combining series and parallel parts until I'm just going to be left with one equivalent resistance, which should come out to 10.1 or 10 ohms. Okay, I'm going to start with these two 5s here. So if I take one of these out, let me see if I can do that. Remove. There we go. And now I'm going to change this one to 10 ohms because these two are in series, so 5 plus 5 of course is 10. And notice when I do that, I'm back to 0.89 amps. Okay. These two here, 4 plus 4 of course is 8. So I'm going to take one of them out. And I change this one to 8. And then I guess I just figured out that automatically it takes off the value, but there it is. So 4 plus 4 equals 8. The circuit, you see these electrons here flowing? Well, they are flowing because it's actually a complete circuit, as you can see. And this one here is just kind of hanging freely, not participating at this point now, but of course I'm going to put it back in. And there it is, 0.89 amps. Okay, these two are in parallel. So what I'm going to do on the side is I'm going to do 1 over 8 plus 1 over 4 equals 0.375, which I invert again, and I come up with 2.666, and so on. So I'm going to take this one out, and this one I'm going to change to 2.67. There we go. Show value. There we go. And then I actually don't need these two wires anymore, so I don't know why there's a junction. Odd. So these two that were in parallel here, 8 and 4, in parallel comes out to 2.67 ohms. And as you had noticed before, when you have resistors in parallel, the equivalent resistance is always smaller than the smallest one. Okay, now these two are in series with each other, so that's a combined 8.67. Okay, and the current is still 0.89 amps. These two are in parallel, and you can see here that junction is the same as this junction, so yeah, the current is going in here. In fact, I could take this off. Let me do that. I'm going to split the junction here. And I'm going to remove this one, put this there, put that there, and notice nothing has changed. So the current coming in here is also flowing out here. Alright, so 8.67 and 10 are in parallel. So I'm going to do 1 over 8.6666 plus 1 over 10. That gives me 0.2153. I invert that, and I come up with 4.64 for these two here combined. So I'm going to take one of them out, and the other one I'm going to change to 4.64. And you see the current is still at 0.89 amps. Okay, these two are obviously in parallel, so 20 and 5. That is 1 over 20 plus 1 over 5 is 0.25. I invert that, and I come up with 4 ohms. And again, my total current is 0.89 amps. Okay, and now all the remaining ones are in series. So I have the one at the bottom, the 4.642857, I still have that on my calculator, plus, turn the value back on, 4 plus 1 plus 0.5, and I come up with 10.14. So if I remove this one, this one, and this one, and change the one remaining resistor to 10.14 ohms. And there we go, 0.89 amps, and the total resistance is 10.14 ohms. And that's an example on how to analyze a more complex series parallel combination circuit. This is a mini lecture for showing Kirchhoff's rules. So here's a circuit out of the book, and we have a couple of batteries here, plus minus and minus plus, and then we have the resistors here, and we cannot put these two in parallel to each other in this one here because the batteries are in the way. So we have to use the alternative, which is the junction and the loop rules. Okay. The goal would be to determine what the currents are that flow through this one and this one and this one, which means we have three variables, three unknowns. So we need a system of three equations. Potentially we could come up with, I believe, let's see, 1, 2, 3, 5 equations, because we have a top loop here and we have a bottom loop, and we have the entire square as a loop, but that one would be redundant because if you put the top loop and the bottom loop together, you get the entire loop. So out of those three loops, one of them would be redundant. And then we have a junction on the left and we have a junction on the right. And I don't know why I just wrote 1 while I said actually 2 junctions. There we go. Okay, I'm going to use the top junction to begin with. I'm sorry, the top loop to begin with. But before I do that, I should label these here. This resistor here probably very likely is going to have plus minus like this. This one here is going to have minus plus. Then again, they could be turned around as well, and we would notice that later if one of our currents, for example for this one here, came out to be negative, then all it means is that I would have to turn these signs around and switch the sign in front of the current. It would be no big deal. The algebra later on will show us the correct results, as well as if we have to turn a couple of these around. Okay, well, 4 here and then a negative 1 here. I want to say that likely this is going to be a positive and this one is going to be negative. Okay, on the top loop I'm going to go up 1 volt. Then I'm going to go down the voltage across this one here, so I subtract. And for the voltage then I use Ohm's law, which is 2 ohms times the current, so this one. And I'm gonna, this is 2 ohms, that's what that one stands for. And here I'm just going to call this I2 according to the 2 ohms. So it's easy to call these I1, I2, I3, kind of makes it nice. And so I go up 1 volt, then I go down, that's the minus, then I go around here, and then I go up, so I add a voltage respectively 1 ohm times the current, so plus 1 I1, and then I'm back here where I've started at 0, so that equals 0. Okay, bottom loop. Let's start here again. So I'm going to go up 1 volt, go down minus 2, down, down, minus 3, I3. And again, I'm adding actually voltages here, but due to Ohm's law, I'm able to write 2 ohms times the electric current, which is the voltage across that one. And then I go up, and I'm back to where I started, which was at 0, so plus 4.0 volts equals 0. Okay. Then I'm going to look at one of the junctions. The current flows from plus to minus, so the current flows this way. So it's going to go into the junction like this. And it flows this way, so it's also going to go into the junction like this. And then it flows plus to minus, so it flows out of the junction like that. And I think we can see that if we did this on the right junction here, that of course these arrows would turn around, but basically we would have the same equation coming up with, and that makes the junction on the right hand side redundant, and we can only use one of them. So left junction, where the current is flowing in, and another current is flowing in, and that current is flowing out. So the two currents that flow in equal the current that is flowing out. Okay, at this point I have 3 equations with 3 variables, I1, I2, I3 everywhere. And so I have to combine them via the elimination or substitution methods and then figure out what the individual currents are. Looks like quite some work. Well, if we recall from algebra, system of equations was quite some work. Alright, on these 2 top ones here, looks kind of like convenient. I could subtract from the other one, I get rid of the 1, I get rid of the negative 2i2, but unfortunately I'm going to be left with an I1 and 3i3 when I did that, and I'm back to actually having 2 variables still. So even though it looks appealing to just subtract this one here, I'm not going to gain anything because I have 2 variables here, 2 variables here, and as I said, if I subtract this stuff here, well, all of this subtracts as well. I'm still back to 2 variables. So I'm actually not going to do that. I believe what I'm going to start out with is I take this I3 and substitute it right in there, because then my second equation is going to be written in I2 and I1 and mimics, in that case, the first one here. So I reduced the first 2 equations to just 2 variables. So that's what I'm going to do. Let's see, so what I just said is I take this one here and I put it in there. Okay, I'm going to rewrite the second equation. So this is the bottom loop combined with the left junction. So I'm going to rewrite that one as 1 volt minus 2i2 minus 3 parentheses I1 plus I2, and that was my substitution, plus 4 volts, I'm going to leave out the units here, equals 0. So that's my second equation here after I substituted that one in there. Notice that this one here is in volts, this one is 2 ohms times current, so that's volts, 3 ohms times current, that's volts, plus 4 volts equals 0 volts. My loop rule is still there. So here then I'm going to combine terms. So 1 plus 4 is 5. Could have done that a while ago. Oh well. And then I have minus 2i2 minus 3i2, so I have minus 5i2 minus 3i1, and that equals 0. Okay, then I'm going to look at the one that I haven't used yet. Let me see if I can use some simple elimination with that one, and yep, maybe I can. Yep, I see it. I'll show you. Oh, I wish now that I could pull that a little bit further down, because here's what I'm going to do. I'm going to use red. I'm going to multiply this by 3 and add it to this one. So 3 times the first one, notice I get 3 minus 6i2. Why did I do that? Because I noticed that when I do that, my last one here is going to be 3i1, and then when I just add that one, I'm going to be able to eliminate the I1. And I'm kind of running out of colors here, so there we go. So add, and I'm going to have 8 minus 11i2 and here I'm going to have 0, yep, equals 0, and therefore I2 is going to equal, well, it's going to be positive 11i2, then divide by 11, so 8 over 11. Oops. And because this one here is actually volts and this one is ohms, it's volts divided by ohms, which of course is amps. And then if I really wanted to, I could write that here as 0.73 amps. Top of my head. Okay, that's one of them. That's the current I2. Now I can take that number and I can plug it in here. So yeah, in this, yeah, I just plug it in any one. I could plug it in here, I could plug it in there, I can plug it in this one here and get I1. I think I'm just going to plug it into the first one here. So let me see if I can move that down. No, not really. So I'll write it again. So the top one is going to say 1 minus 2 times 0.73 amps plus 1 I1 equals 0, and then I solve for I1. Okay, let's see what I get. First of all, I'm going to plug in actually 8 over 11. My calculator 0.7272727 and so on, and I multiply that by 2. So this part here becomes positive because it goes to the other side, so 1.45. Then I subtract 1, so I come up with 0.45, and I divide by 1, which is still 0.45, and that's my current I1. As far as the units go, let's see, this one here actually is ohms times amps, which is volts, and then to the other side, still volts. Subtract volts, still volts. Divide by, this is actually ohms, so volts divided by ohms, of course, is amps. And then I3 is going to come out to those two combined. So point, this one here, I1 plus I2. And that one is going to be 1.18 amps. So those are the three currents that are flowing through here, and notice all of them came out positive, which means my initial choices of plus and minus on here were indeed correct. I think these two here were more or less obvious. And this one here was kind of obvious too, because of the 4 here being quite a bit stronger than the 1. But even if one of them had been negative, all it would have taken is take the negative away and switch the corresponding plus minus around. So it wouldn't have been any big deal. All right, we actually looked at quite a bit of algebra here, and you may recall from doing systems of equations that you can achieve the same by doing matrices. And that's what I'm going to show here. I may have to zoom out a little bit. Hold on. Let's see, zoom. There we go. Okay, that might be just enough space. Okay, I have three variables, I1, I2, I3. In my first equation, I have 1 I1, I have negative 2 I2, I have 0 for I3, and then on my right-hand side of my matrix, I would have a negative 1 once I bring it over. Remember, this is how you do matrices. On this one here, I have negative 2 I2, negative 3 I3, no I1, and I have 1 plus 4 is 5, but I have to get it to the other side, negative 5. And on this one here, I have 1 I1, 1 I2. I have to get the I3 over, so that's negative 1. And once I get that, I have 0 on the other side. So there it is. So what I did here is what you had done in college algebra before. And therefore, I'm not going to get into detail here. This one here, I'm going to transform into this kind of matrix. Where all of the ones correspond to the variables I1, I2, I3, and then I1 equals, I2 equals, I3 equals, and we'll see what we come up with. And the reason I do that is to show you an alternative method to the system of equations, and to show you that that one, of course, can be done quicker than doing all the algebra. The system of equations, so here's 3 by 4 matrix, and 1, negative 2, 0, negative 1. At this point, of course, the only thing I could do wrong is put in an incorrect entry, but then again, that could happen, so I have to be careful. And I'm going to check this one. That one looks right. If over here I have written it down correctly, that it says here negative, 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 I could change this to positives, but I'm just going to leave it like this. Okay, do the math, double REF. We'll solve my entire matrix. Oops, oh, I chose REF, I meant double REF. I said so and clicked accidentally on the wrong one, so try that again. And there we go. And when you look at those, and when you look at those numbers, they're the same as what you have over here. And in fact, I'm going to make it easy on myself. Nope, there it is. That's the one. I paste it in there. There it is. And then of course these are amps, amps, and amps, and just the same numbers that I calculated with the system of equations. And then I do want to show this using the applet. So okay, one resistor, and I put the ammeter right next to it, and another resistor, and the battery, and that one should be correct here, and this one is 1 volt, and then another battery, and this should be turned around, and that's 4 volts. Ammeter, and here we go, and let's see, this one is 3, 2, and 1. And connect with the wires. Oh yeah, show values. There we go. Alright. Combine them all. And I think this is going to be actually really quick. There, we're done. 0.48 amps. I'm sorry, 0.45 amps, 0.73 amps, 1.18 amps as calculated with the system of equations, respectively, the matrix.